I know it's kind of getting, close to the end of the whole next, and I've got a lot of stuff to talk about today. What you should never do is name your talk 10 of anything, right? Maybe a handful or a few or some, but don't commit yourself to like a big number or anything. So we might go kind of fast, but hopefully I'll keep you awake after lunch. My name is Luke Stone. I am from the Customer Reliability Engineering team, and what we are is we are Google SRE, that's Site Reliability Engineering, for your applications, right? So today we're going to talk about 10 common causes of downtime and how to avoid them. So this is, first I just want to get into just the ground rules of what we'll talk about today, because this is a pretty big topic, right? It's kind of like complementary to Miles Ward's talk the other day that he did to the IT and ops track about how to make and run reliable applications. This one is for app developers, and it's really about thinking about how you can design your applications and the features you want to put in them so that your applications stay resilient automatically, and you don't have to yell at your operator to go fix it, right? So I'm going to present just a list of 10 things that I've seen in my experience, and we'll go over some ideas about how to prevent them. These are not things that you'll see everywhere, but these are things that I've seen myself. So a little bit about me. I've been at Google since 2002. I started off and I came in doing technical support for AdSense partners, and this was one of Google's first partnership types where it was a technology partnership. We sent ads to our partners over XML feeds over the internet, and they put the ads on their website, and then we shared the money. And it worked really well, but it needed to be up all the time. And it really taught me this lesson that, if you're in a technology partnership, the thing needs to be up. Both teams are responsible for it being up all the time, right? It didn't do me any good to point my finger at the partner when the ads were down. We just had to work together to get it up. I've been in GCP since 2014. I started off in GCP running the tech support org. I see you guys. Yeah. And we do great tech support at GCP, and we have really good engineers who are 24/7 doing tech support. And what I found during those couple years of running tech support was that people are looking for really high reliability, like 4 nines, 5 nines. You kind of can't get that if you have to file a ticket with tech support that costs a couple minutes. If you have 4 nines is 4 minutes a month of downtime, right? So you're blown away as soon as you're filing a ticket. So we need to think about how we can make the application reliable, automate recovery, be resilient, auto heal, so that we don't have to ever file a ticket, right? And that's why we invented CRE, which is Customer Reliability Engineering, so we could get this done. So basically, outages like this, you can see queries per second start falling off a cliff, and the latency goes to basically the max. That kind of outage that you might have, once a year, that's my day job. So if I can see all these different outages, spot some patterns, and then share with you guys, I think I can provide some pretty good value. Okay, so what we'll talk about today is not super not super secret or anything. A lot of it is basic distributed systems stuff, but you need to think about the stuff, even the basics, and really do every single thing that is going to break your application before it does break your application. And we also have to think about not waiting for ops to come along and clean up afterwards, and not get to a spot where, I ran out of computers, I need to call ops and get some more computers, right? Your application needs to be built in such a way that it can provision more resources when it needs to. It can notice when it's at capacity or it's down. So the first priority is keep serving traffic all the time, keep serving traffic. And then raise an alert so someone can come and remediate the situation later, but do some graceful degradation. And also these things are not super tied to GCP products. This is broadly applicable on-prem or on another public cloud. Also, these are just kind of generic patterns that we see, and there's no reliability product. Reliability is just a result of lots of hard work, lots of planning, having really good design and good practices. You can't just go buy the reliability button. This is actually pretty different on public cloud than it is on-prem. There's actually a lot of companies out there that will just try to sell you reliability for money with appliances that you can buy on-prem. But that's not really how it works in public cloud. So you need to change your thinking a little bit away from this scale up and we'll just, add 4 more redundant power supplies and this kind of thing. And think about how we're going to scale out, how we're going to anticipate that nodes are going to go down, and we'll be able to notice that and recover automatically. Okay, so we'll think about an example application, of course. How can you do this kind of thing without any kind of example? Imagine you're a Muppet and this is your app. Okay, here's this architecture just to lay it out. It's pretty simple. We have an API backend that we're developing. We have some users. They're represented by the U. Okay. We have a load balancer. That's the LB. Your API backend is the A. This is kind of the thing that you're coding. And then you have an external service, which is, I called it a vision API, right? It could be something. But you're calling to it, and it's not under your control. I've made the sizes of the dots represent the capacity of that node, right? So if it's users, kind of think about it's enough users to generate 100,000 queries per second. And queries per second is a terminology we use in Google. It's kind of comes from our days in search, where people are doing queries. So a lot of people say requests per second. We just use this term queries per second. So the size of the nodes is capacity, and the size of the edges is traffic flowing along them, right? So if the edge gets bigger than the dot, we're in trouble, right? Think about that. And if the edge gets a lot smaller than the dot, that means we're not serving to our capacity, and that's probably a problem also. Okay? So, number 1 cause of downtime is you just get overloaded. You have a success disaster. Imagine you launch a really great video game and people really like it 50 times more than you thought they would. This happens all the time on cloud because we have really great networking and scaling all around your application. So where you may be used to on-prem, have a little drinking straw firewall or load balancer in front of you, or little drinking straw internet connection, that will shield you from all sorts of load problems, right? You just kind of don't see them because the packets get dropped outside and users are complaining, but as an application developer, you never know it, right? On our cloud, it's really different because the load balancer is super happy to send you millions of queries per second. It loves to do that. The firewall is distributed, as you probably know if you've read the Andromeda paper, the firewall is distributed and it's actually on all the hosts. So it can take any amount of traffic, right? And the network is really well connected to the internet, so you really don't get into a situation where users can't reach you because you don't have bandwidth. So here in this scenario, I've made the users 3 times as big. They went to 300,000 QPS. Now your application is getting overwhelmed, right? It can't keep up with demand. It can only actually make 10,000 QPS back to the Vision API. So this is all of a sudden, this becomes your effective throughput, is you can only do 10,000 QPS back to the users of useful work because you're sitting here dying under all their load, right? So I hope you can see that kind of at the bottom of the screen. You can see the node that's selected has a blue circle around it, and you can see the edges coming out of there. So what do you do about an overload scenario? Do you call the ops person and say, hey, add more servers? that's going to take a lot of time, right? There's no way. So what you need to think about is, I'm going to shed the load. I'm going to get rid of load that I can't possibly serve anyway, so that I can serve a little more valuable work, right? So think about, the types of traffic you're getting. If there's a type that's not as valuable as some other type, maybe like toss that on the ground first. Just very quickly, serve an error, right? Because you're trying to just defend yourself at this point. Just trying to get rid of enough work that you can do some useful work and not just die. So one way to think about this is to just calculate the capacity of your service, like using a load test or math, and figure out, okay, I can do, if I can do 100,000 QPS at my application server, then everything over 100,000, I'm just going to keep a counter, and everything over 100,000, I'm just going to return an error just immediately, and it's going to cost virtually nothing, right? Then at least you're serving some useful work. So it's a way to artificially increase the capacity of your service. And you can actually serve a nice error to your user that tells them something, better than just like TCP timeout, right? It's pretty good. So the problem here is that we're serving nice errors to our user, and we're saying, yeah, like our site's having a problem, and there's like a little, sad Tweety bird or something, but we're still only getting 100,000 QPS of useful work out of the Vision API. So it's not great, but like we're still serving some traffic, and it's not the end of the world, right? So that brings us to our next cause of downtime, right? Which is that you get a noisy neighbor. You did all this nice work to compute that your service can handle 100,000 QPS at the application layer, but you forgot about the fact that you're going to be running a backup script on that server, and that's going to take up a bunch of cycles, right? Or you have users, and as soon as you have users, you get spam, and you're going to get spammy users, and I guarantee you'll be shocked at the size of the spam compared to the size of the real users, right? I mean, it's very easy for the spam to go 10x the normal the normal volume of the actual human users. So you really need to protect yourself against this stuff. So if we just shed load evenly, like just A, B, I'm just going to decide to shed, then we're going to actually impact our real users a lot more than we need to, because we can actually be a little bit smarter about it, and we can decide which queries to throw away. So the way to think about dealing with noisy neighbors is you put in place limits. Like you say, artificially limit, each user ID is going to get 100 queries per second. I can't imagine a human user would do more than 100 queries per second, right? And that really helps because a lot of the spam bots, bad guys will be sending 100,000 queries per second, and that's really more than is reasonable. It's easy to detect. Some people try to do stuff like do it by IP address or something, but you have to check your assumptions a little bit about how distributed the load is across IP space. If you have something like a cookie that you're giving out, then you know a little bit more about the distribution of the key space. So using user ID, using a cookie ID, using some hash of a bunch of information that you can get from the HTTP request is pretty useful way to keep counters on how many queries people are allowed to do, and then cut them off when they hit their limit, just to protect others. So it's also good to do this in combination with a lot of different similar strategies, like limit the cookie to 100 queries per second, and then maybe limit each IP address to 100,000 queries per second, and then maybe limit each user agent to 100,000 or something, and then you can kind of build a layered situation where it's likely that you'll take out a bad guy before they get all the way through, right? But inevitably, you're going to take out some good guys too. You'll still be serving 90% of the good guys, so that's good news. But somebody will complain, and they'll say, hey, you took down my IP address, and I'm really mad. Why can't I access your service? So make sure that you make these things configurable, and don't just like hard code it into your code where you'd have to like deploy new code in order restore service to your users, make it configurable so you can just push up a new file and let them back in. Most users will say, yeah, I'm bummed, but you said you were sorry and you fixed it right away, so thank you so much. They don't really like it if you say, I have to leave you out of service for a week because of technical issues on my side because I have to burn a new release, right? They don't care. And you also can just alert again to your ops team and whack the mole later, right? By pushing a firewall rule or something up to a higher layer, so it's cheaper to serve or it's cheaper to reject the bad traffic. First things first, though, is just protect the service, protect the good users, and keep going, right? So what happens when you start rejecting people? Well, they retry because they don't know why they're rejected. So retry spikes are a pretty famous way to generate a lot of load. And when you're dealing with a microservice architecture, it's pretty different because each layer is retrying to the next layer, right? So you can get this compounding effect pretty quickly. I've just illustrated here 300,000 QPS provisioned at the API server, and the users turns into 2.7 million after it gets compounded 3 times by the client, and then the load balancer is retrying again. And you can imagine what happens if you put caching layers and stuff in between here, right? It can get out of hand really fast. So watch out for your retry spikes, because this is the most common cause of a cascading failure, is that some little part of it goes down, and then everybody piles on and tries to get more, really crushes that thing, and then they move over to the next zone or region, whatever your deployment unit is, crush that thing, and nobody can get back up because there's just so much noise from all the retries. So what do you do about retries? Well, this is about the client and the server actually being polite to each other. A lot of it has to do with the client. If you can control the client, you're very lucky. Usually this is like mobile application scenario. You can control the client a little bit. There's a lot of time-honored techniques of doing backoff, and we did a CRE blog about backoff. The classic is like exponential backoff with jitter. There's kind of no reason that exponential backoff is the right amount. There's no reason you should wait 1 second, then wait 2 seconds, then wait 4 seconds. Maybe you wait 1 second and then you wait 10 seconds and then you wait a day. It really depends on your application. Even with an exponential backoff of waiting 1 second, 2 seconds, 4 seconds, you're still getting 3 retries within a few seconds. It's unlikely that you've actually fixed your service in those few seconds. So think about having your backoff in terms of the time that you expect your service to come back online, right? There's also signals you can send to the client from the server. You can say, hey, please try again in an hour or tomorrow or something like that. There's a HTTP header called retry after that nobody uses, but you can. And when it becomes available in browsers, then it'll work. Another really powerful technique is to implement a retry marker from the client. So the client says, hey, this is my first retry. Hey, this is my second retry. Put it in a URL parameter, right? So then the server can see it, and they can say, okay, I'm going to decide how to shed my load, and I'm going to rank it by the number of retries you've had. So if you're on your 5th retry, you've already given up anyway, so I'll throw those away, and then I'll throw away all the 4 retries, and then I'll throw away all the thirds, but I'll be really careful to serve all the first ones that I see. So that's a pretty powerful mechanism. Another mechanism that's useful as a last resort is tar pitting, where what you do in the server is you just wait and you introduce some artificial latency so that the clients can't retry very fast. So you basically try to use up as much of their timeout as you can get away with, and then return to them, right? Even if you're returning an error, you just wait and then return. So you're kind of stringing them along a little bit, but it's something you can do purely on the server side to slow down the request velocity. Okay, so we were going right along, and we were serving nicely until our Vision API, which we thought could do 100,000 QPS, all of a sudden started doing like 10,000 QPS because it just got really slow, and we don't know why. So now requests are piling up at our API server, right? And now we're ooming, and now we're not serving any traffic back to the users. This is just terrible. The problem here really is that the input and the output of your service are kind of clueless about each other, right? So the solution is to make the logic that's accepting incoming requests be aware of its ability to service those requests via the external dependencies on the back end. So if I can only do 10,000 QPS of the Vision server, I should really only be accepting 10,000 QPS in the front end, right? So the original load shedding, technique that I suggested of just deciding that you could serve 100,000 QPS and then just throwing away everything after that, Adrian Hilton, who's one of our CREs, he called that Procrustean load shedding. Procrustes was one of Poseidon's sons who ran kind of a gloomy B&B where he had an iron bed, and people would come and he would welcome them in. He would say, "Oh, I have a bed that will fit you just perfectly." And then if the poor sap was too short, he would stretch them, and if the poor sap was too long, he would crush them. And so it became a term that's used for taking the problem and fitting it to a known constraint, even if it doesn't make any sense at all, right? So luckily, Theseus came along and dispatched him one day, so we don't have to worry about him. But we still can't also rely on that as a load shedding technique, because when your capacity kind of approaches zero, then your assumption that you could serve 100,000 QPS is wrong, and you fall on your face, right? So we need to think about being really defensive in our client, and your client needs to become like a defensive driver, right? Like leave a lot of space, make sure that you're not going to overwhelm your backend dependency, and tell the upstream that when it's time to back off. So you need to think about what are the timeouts that my clients are making to me or having to me. Like if they're going to time out after 1 second, like don't set a 3-second timeout on your backend, because by the time you get an answer back, your client's already gone away. So you need to kind of, you can work this through in just your mental model of how the system works. It's very much cheaper than figuring it out in real life. And it's also really nice to just be able to, okay, just abort your backend connection after a second very cheaply if the client's already gone away. But how do you know when the client's going to go, when your dependency is going to go away? A lot of the dependencies operate really, really well most of the time, right? So like cloud storage is a great example. It often has like, tens of milliseconds latency, and it's 4 nines for many weeks. And then by design, someone does some maintenance and it goes up to 80 millisecond latency and 3 nines, which is like the published SLA for it, right? But if you've been just relying on it to work kind of how well it's been working in the past, then you'll be very surprised. So what you want to do with that is do a disaster test where you simulate the worst possible expected behavior of the service. So you can put in logic in your client to your backend that artificially slows it down and makes it look like the backend is bad, and then you can see what your clients are going to do to react to that. So that's one technique, and of course, just doing good load tests will often tease a lot of this stuff out. Especially doing load tests that are very sudden and spiky. I mean, I know a lot of people do load tests where they kind of gradually ramp up the load, and that's great because it's a very safe way to do load tests that's unlikely to come up to like find a problem. But the purpose of the load test is to find the problem. So simulate the scenario that you would have if you had a zonal failover or something, where you all of a sudden get a huge instantaneous load. That's the most fun type of load test to do. Then you'll really find the problems before they occur in production. The best possible scenario to implement is like a dynamic load shedding, where you can actually decide how much load to shed on the front end based on how your back end is performing, and have some equilibrium heuristic in your service that can just adapt all the time. That way you can kind of get the best performance and the best availability all the time. And one thing that's kind of close to that is being able to at least manually adjust your client parameters. I know a lot of people just put in, retry 3 times with a 1 second timeout. Just make it so that you can configure those. That can really save your bacon when your client is being too aggressive, to just be able to push a config very quickly. Within a few minutes, you can have your client back off really nicely. Okay, so all of that was in the scenario of you have like one VM serving your service, right? And all of those things are terrible things that can happen to your service, no matter how big it is, when you have 300,000 QPS of demand and 100,000 QPS of ability to serve it. So let's say we actually want to serve that 300,000 QPS. The bottleneck here is between our application and this external API, right? So what do? We get a bigger VM, right? That's not a very good answer, actually. So the cloud is really built to scale out. The thing that's different with the public cloud that's from your on-prem is that we have really good network. So adding new nodes to the network doesn't really cost anything in network space. You don't have like this VLAN problem. And provisioning new instances is super cheap. So take advantage of that and use it. A lot of people have deep, horrible scars about asking for a new machine and then having it take months to provision. And you need to erase that from your mind. And this is a beautiful new world where you can have a new machine in seconds. So make sure that your application actually calls those APIs and makes that happen when it's necessary, because it's not going to be the last time that you scale up or maybe scale down. So you need to think about how are we going to scale past the boundaries of the components of our system. So VM is one. Like a Cloud SQL instance is another pretty obvious one. Even like a GKE cluster will have a size that it can't go beyond a certain number of nodes. And there's some strange scaling boundaries too. Like in App Engine, you have a scaling boundary at your request deadline. It can't go for more than so many seconds, and it can't use more than so much memory, depending on the type of request it is. So there's a bunch of different scaling boundaries that you might have to like anticipate and think about, but the answer in all cases is the same: scale outwards. So how do we do this? At Google, the term we use is sharding, and there's a lot of terms across the industry for this, and they're all describe the same technique, which is you take a consistent workload and you divide it up into little chunks that can be done independently, right? It's just divide and conquer among a consistent workload. It's different from the noisy neighbor scenario, which is more about different workloads that were coincident on the same resources, right? This is the same workload that you can split up. So if we take our server and our API server and just replicate it 3 times, then each one of those can do 100,000 back to the Vision API. Then we can serve our full 300,000 to our users, and everything's good, right? So we use more shards to increase our capacity. What do you use VM sizes for? Why do you even have that? Well, those are really good for getting best performance and efficiency, right? So if your unit of work lends itself to having 1/4 of a terabyte of data in RAM, then you want to pick a machine that's that size, right? But you don't want to just have that unit of work be just growing over time as your inputs grow or something like that, right? And sharding is really hard. It's very difficult to take your chunk of work and figure out how to make it independent across multiple machines. So start super early on this and think about it a lot and try little ideas and prototype a lot to get the right balance. So it takes a while, but the best practice is as soon as you find yourself wanting to crank up that instance type and make it a little bigger, file the bug to implement the sharding and keep it pretty high on your backlog. So after we shard, we're all super happy because we know that every single one of our instances is going to get 100,000 QPS, but of course that never happens. One of your shards is going to get super busy, right? One of them is going to have the celebrity on it, or it's going to represent New York or Tokyo if you've sharded across geography or something like that. So one of them is going to get hot. So think about, how am I going to balance that out after it happens, right? You're going to need to re-shard. You can't just hope that they're all going to be balanced out. That's the SRE motto, actually, is that hope is not a strategy. So how are we going to reshard? Well, one of the things that you can do is implement a shard map. So it's not a static sharding from the data to the ID of the node that's serving it. It's actually a lookup table. So you can put something in the middle, right? And you can even use that technique to like get one hot key and put it somewhere else. It's more complex because you have multiple nodes this time. So it takes a little more work than just pushing something to a single node. Like you might be able to get away with resharding a single node at a time while leaving the other ones together. And that is what we call splitting a shard. This is like the primary technique that's like the go-to move if your shard gets too big. It's just split it in half. This is how Bigtable works. It just waits till the shard gets too big and then it splits it in half and then does it again. It's not super reliable. Like if you have one key on the shard that's super hot, splitting it in half won't really help that much. But it works in a lot of cases, so it's a good way to start. One of the nice things about splitting shard is you can just do it just with that one shard, and you don't have to worry about the rest of them. You can just kind of keep them running, and you don't have to like update your global shard map or anything. So I recommend it. And if you have a super hot key, probably resharding it is not going to actually help. You probably need to think about moving that out and making it a separate workload or separate subsystem, like put it in a cache or make a dedicated subsystem that can actually serve that thing. If that thing itself is 100,000 QPS, you might want some special attention. Okay, the end of the pretty pictures. So what we say in the cloud is that we prefer cattle, not pets. And this is just how we think about the subsystems that compose our service. The classic one is a VM, right? So a pet is a nice thing, and you probably have some subsystems in your service that they have cute names and everybody knows what they are, and people refer to them by name. And if they die, then you cry. You're very sad. But if cattle dies, it's a cost of doing business, and that's kind of the way we think about it. I was always really impressed when I first got to Google with how little tears were shed when a very important machine went down. There was just a script that you ran that was just like throw away the machine, and it would just take the machine out of all the configs and send somebody in the data center to go physically fuss with it. And it made a lot of sense once you got your head around it, that as soon as you detect there's something wrong with it, don't try to fix it, just get rid of it, because you have another technique to actually auto heal or bring another one back into the herd, right? So pets are often one of the hardest things to deal with because of the human factors around them. A lot of pets have like a handler, and you probably know some of these in your systems where there's a certain person and they're the only person that knows how to deal with this thing, and it gets very upset if anyone else touches it, and so we leave it alone until that person comes back in the office, and everybody's very scared, even though they realize it's absolutely critical for running the service. So if you see that kind of thing happening where people are scared to touch a machine, that's a good sign that it's a pet. And Also, when you see people trying to be heroic around their pets, and like be the fireman who like goes and saves the cat from being stuck in the tree, that's a good sign that you have a pet also. You should just let the cat get down from the tree by itself if it needs to. There's other cats, right? Sorry. So the best tools I know for getting rid of pets are just acknowledging that there's a pet, right, and documenting it. And once you've written it down that this thing is critical and nobody knows how to deal with it, and when it breaks, our whole service goes down, it starts to sink in, and people get over their fear and start working on solutions. So I definitely recommend writing it down. You might have experienced this. Outages often occur when you change something. So don't change things, right? This is the number one cause of outages in every system that I've ever worked with, is people deploying something. At Google, we think of the config and the code in our system as really one and the same. We don't really treat them any differently. In terms of how we manage them in the source code repository, we put all the config in the source code repository, and we do rollouts of config and code in very similar ways. Config, it's kind of like config is just like code that can be pushed out with greater frequency or something like that. And we treat config like code by like unit testing it and sanity checking it just like you would with code. So the best techniques for not deploying bad code are to have a good way of recovering when you do, because it is just so inevitable. A lot of the time, people will try to fix something hot after they push some bad code. They'll try to debug it and fix it. And the absolutely most important thing to do is have a tried and true rollback process where you just have a big red easy button and you can just smash it as soon as you notice anything going wrong while a deployment's happening. So precondition for that is you have to know when a deployment's happening. At Google, we have a database where everything that deploys something posts a record into this database, and so you can kind of go and look it up and see if something is see if some component is changing that's related to the alert you're getting. And you probably want to do something like that too. You can, people do stuff as simple as like a Slack bot that just, records every deployment that's happening, to using something that's pretty advanced like Spinnaker, where you can actually see what's going on and control it. But the most important thing is, when operator A on system A is noticing that something's going wrong, they look at A's 53 dependencies, they can see which ones have changed, in the past 15 minutes or something. And it allows you to then hit that easy rollback button on the right system. It's not bad to hit a rollback. We often roll things back and then roll them forward again, not much later, because the rollback, it was like a false alarm. You roll it back, you end up kind of delaying the progress of the whole rollout by, I don't know, a couple hours or something. But it's really good peace of mind, and it's a really good thing to just to get in the habit of like muscle memory of just doing it, right? So once you have that and you're really confident that your rollback works and you just hit it every time, you can start to automate your rollbacks by having something like a canary watcher that watches the first machine that gets your new code and sees if it goes error condition. If it goes error, it just stops just stop and roll back. Take that machine, take it out of the service, and then you can do forensics on it, whatever on the side. I said canary, that will probably give the idea that progressive rollouts are a really good idea. So you think about just sending it to one machine first, and then maybe 10 machines, and then maybe a whole zone, right? Then maybe a whole region. And the rule of thumb you want to do is you want to go slowly enough that you can detect the issues that will emerge, right? So you don't want to just kind of like run through those stages automatically. You might want to go a little faster from one machine to 10 machines than you do from zone to region, because you have to give yourself time to like figure it out. Like for example, one thing that people often do with the global system is they roll it out globally too quickly. Like if you have your roll done into a region and it happens to be sleepy time in that region and you don't notice because all the users are asleep, right? And then you go ahead and you roll it out globally and then the users wake up and then you realize you have a global outage on your hands. So just go slowly, make sure you have a good bake-in time for each stage of your progressive rollout. But if you need a rule of thumb, a pretty good one is to do like a 1%, 5%, 10%, 50%, 100% kind of strategy to ramp up. That gives you enough easy ramp time in that you'll probably catch most of the problems on the first machine, right? You often don't know if it's just the machine itself or if it's the new code, but by the time you get to 50 or 100%, you can actually go pretty fast because you've already done a few increases. The main problem people have with doing progressive rollouts, though, is that they don't really understand whether the new software is actually working correctly or not. And this is because a lot of people have monitoring gaps in their system between what the user's expectation is and what the monitoring is showing. So it's very typical that people will be monitoring CPU and RAM usage on a server, put some new code on it, and then they see the CPU and RAM usage changed a lot. And then they kind of wonder if that's a big problem, and then some time passes and then they decide it's not a big problem, and then they just kind of let the rollout go on, right? And maybe it is a big problem, maybe it's not a big problem, we don't really know. But the real test is, did your users think it's a problem? So the ideal scenario is if you can have a monitoring metric that actually predicts your user's opinion of your service, right? So it's not that hard to think about how many errors are you serving, was there a big change in latency that you're serving? A lot of times you'll add new features to your service over time and your CPU usage will go up quite a bit when you put on a new feature, or it's very common that a new feature will have a new data set that it needs to pull in. So you push out your new feature, it does a whole bunch of I/O and a whole bunch of CPU to pull all the data into RAM and put it into 40 different tables so it can serve. And it looks really scary to the operator, right? Because you just put some new code and it does all this stuff and you don't understand. But the most important thing is, did you think about exporting a metric about the success of that new feature? So you can see if that metric is trending like you like. So then if you detect that the users are unhappy, that's when you dive down to your CPU and network and RAM stuff just for diagnostics, try to give you a clue as to what's going wrong, right? The most useful thing you can do is build these types of metrics right into your microservices libraries. So in Google we have a RPC layer called Stubby, which it gives you a client stub and a server stub. And it's great because the client stub exports how many requests it's making to the server, and the server exports how many requests it's getting. And they have consistent definition, and they operate on similar pipelines, so they arrive at the same time, and so you can just make a graph of like how many did the client send, how many did the server get, and it's like dead easy to tell if there's like a network problem, right? So a lot of services I see being built, people kind of try to monitor on the side, or they try to monitor off of logs or something, but it's really, really, really helpful to build it into your network client and server libraries to export these high-level metrics right to your monitoring system, so you can really tell if something's going wrong. This is the last one. You made it. You really need to understand what are your failure domains. And these are chunks of your infrastructure that can fail all together at the same time, right? So obviously a VM can fail, and all the processes on that VM are gone, clearly, right? And obviously a zone and a region have, they're also failure domains that we talk about explicitly, that we want to think about. if you know your failure domain, then you can do really smart things like put your backup in another failure domain, which a lot of people kind of don't do for some reason. But it's really important to be thinking about where am I going to actually recover from when I need to recover. A lot of outages I've seen get to a point where people are thinking of, oh, should I stand up, should I stand up a new cluster in a new zone because this one's down? And then they start thinking, well, which zone should I choose? This is a decision you can make way beforehand, and you can choose what's your new failure domain going to be and where you're going to recover to, like way ahead of time, right? And put your backups there and put all your data there so you're ready to go. You don't have to make any decisions. Making decisions when your system is down is the worst possible scenario because you're all full of cortisol and you're crazy, right? So just try to make as many decisions as you can ahead of time. And you want to use your failure domains for a lot of your day-to-day operations, right? Like make sure that your failure domains are in your monitoring, as a dimension that you can cut by. Because if a zone goes down, then you want to see that zone went down, not just like nodes 1 through 49 went down, right? You want to use it also in your rollouts. So you want to roll out to this zone, and then that zone, and then that zone, because if the zone goes down in the middle of your rollout, you want to be able to be sure that it's the zone going down and not your rollout taking it down, right? If you imagine if you rolled out to multiple failure domains at the same time, then it would be a little harder to tell what's going on, right? And you want to actually disaster test on the edges of those failure domains. So we like doing destructive disaster testing at Google, and we'll just we'll take a node and shoot it, and just like the whack-a-pod kind of thing, or we'll take a whole zone and just knock it out and see what the operators do, see how the system recovers. So it's a good boundary to think about. And you can also make failure domains within your application, like synthetic ones. So you could make you could have your power users be in one logical failure domain, and then everybody who signed up yesterday be in another one, right? So that you can think about what would happen if we sacrificed those people. Would we still be getting a significant amount of traffic from the rest of them or not, and what would happen? So you can get kind of creative about how you fail. All right, we made it. So we know all that stuff. A lot of it is not super rocket science, and a lot of it is stuff you've probably seen before and heard before. But it really is important, and it bears repeating. So how do we actually get the 9s? Just knowing about the stuff is not worth it. It doesn't give you automatically 9s. You have to act on it. There are hundreds of bugs out there which are just little time bombs waiting to go off because someone knows that there's a problem and they can't really justify putting in all the work to fix it right now, right? So a good technique to think about that is think about the criticality and the impact of the problem and how likely it is to occur. So is it a critical situation that's going to take your service completely down, like if your pet dies? Or is it something that's going to maybe degrade your service, or maybe you won't even notice at all? And then how frequently is it likely to happen? Is it going to happen multiple times during a single on-call shift, or is it going to happen maybe once a month or once a year? And then you can think about quantifying how much time it's worth to actually invest in these things, and then scheduling out the time over several weeks or months to actually get some of these bigger chunks done. There's been far too many outages that just went like, oh yeah, I knew that was a problem, and we've known about it for 2 years, but we just never bothered to fix it, right? And that really comes down to just analyzing stuff. I'd like to remind the developers that reliability is a number one feature of your application, is that it works. And so it's completely legit to file a bug and say there's a reliability problem, and have a discussion with your product managers about, where do we actually put this in the features, right? Do we put it at the top? Usually it comes pretty much to the top. I found most product managers say, oh yeah, of course, obviously, I thought you were doing that all the time. right? But it's good to have that clear, conversation about it to make sure that you actually get to it in time. So these are things we can actually anticipate and prevent because they're fairly generic and they'll pretty much happen to everybody. But of course we can't anticipate everything. So we're going to fall back on a lot of our SRE principles and practices to deal with all those things, like do a blameless postmortem, do your disaster testing, do your reliability reviews, by actually, what I mean by that is get the design ready, talk about the SLOs and what are the requirements, get a bunch of disinterested engineers, colleagues or friends in the room to try to poke holes in it. And make that as part of a practice, and that's the way to get those incremental improvements for these weird things that you can't really anticipate. That's going to be the thing that's going to take us forward to 3 nines and beyond. All right, thanks for your time, everybody.